Hello and welcome. In this video, we will learn about separation of variables. Separation of variables is a technique for solving certain differential equations that are called separable differential equations. And before we get into actually looking at this technique of solving these differential equations, let's do a little bit of review to make sure that we're really comfortable with all the concepts that we've learned about differential equations so far. So we've seen that a differential equation is an equation that contains some unknown function, and usually we call the function y, and one or more of the function's derivatives. And we've talked about the order, that's the highest order derivative that appears in the equation. A solution to a differential equation is a function that satisfies the differential equation. And we've talked about the concept that there is no systematic method that always works for solving differential equations. This is sort of like integration techniques. Certain integrals can only be solved using certain techniques, and other integrals just can't even be solved using really any technique except a numerical technique. So we have a similar thing with differential equations here. There are many different techniques for solving different types of differential equations. We will only learn one technique that only applies to a certain special class of differential equations, and this technique is called separation of variables. So far we've seen a graphical approach to looking at the solution for differential equations with slope fields. We've seen a numerical approximation technique with Euler's method. And finally, in this video, we'll actually see an analytical technique for solving certain types of differential equations. Let's take a minute to think of the connection between differential equations and the solutions. So here, we've seen this table before, but here we have a bunch of differential equations, and we can think about the order here. This first one is first order. This is also first order. Then we have third order, and finally, this is a second order differential equation. And the general solutions are written right here. And I've mentioned before that we shouldn't really worry about where these solutions come from. We haven't seen the techniques for finding these solutions. And in fact, for these last three examples, we won't even really see the technique. This first one we can solve using the technique that we're about to learn. And actually, we could modify this second one to solve with separation of variables. But these other two, really, we're not going to have any idea how to solve them from just talking about separation of variables. So here we're going to start out with differential equations. And as long as they're the proper form, as long as they're the proper type, we will be able to solve them using separation of variables. So we'll start with a differential equation. And using this technique, we will be able to come up with a solution. So let's talk about the kinds of differential equations that we can solve here. These are called separable equations. A separable equation is a first-order differential equation that can be written in the form dy over dx equals some function of x times some function of y. So this is first order, first of all. And we can write the derivative dy dx, or we could also write this as y prime if we wanted. We can write the derivative y prime as a function of x times a function of y. So we have to have a product here, some function of x times some function of y. These differential equations can, at least sometimes, be solved using the technique of separation of variables. So before we look at the steps of this technique, let's take a look at a couple of examples of separable versus not separable differential equations. Here's an example of a separable differential equation. dy dx equals sine of x times y squared. I've written the derivative as a function of x times a function of y. Now here's an example, so this is separable. Here's an example of a differential equation that is not separable. If we write y prime equals, let's say, sine of x plus y squared. Here, I don't have a function of x times a function of y. I have a function of x plus a function of y. So this would not be a separable differential equation, and we could not solve this using the technique of separation of variables. So before we use the technique of separation of variables, we have to make sure that we have a differential equation in the appropriate form. This technique will only work for separable differential equations. So what are the steps? How do we actually solve a differential equation using this technique? The first thing to do is to separate the two variables. So we separate the y's to one side and the x's to the other. So here's the general form for a separable equation. dy over dx equals some function of x times some function of y. And the way to separate this out is to move all of the x expressions to one side and move all the y expressions to the other side. And we're going to handle this dy dx, the derivative, as if we can split up the notation. We won't work through all the details of why that actually works, but it does in fact work for us to split up the derivative as if it's a fraction. So we can think of multiplying both sides by dx, divide both sides by g of y. If we do that, we will have 1 over g of y dy equals f of x dx. Notice that I've separated the variables. All of the y's are on one side, and all of the x's are on the other. So this is why it's called separation of variables. I separate the variables to the two different sides of the equation. So after separating the variables, I have 1 over g of y times dy equals f of x dx. Once we have done this, we integrate both sides. As long as we can write the differential equation in this form right here, and then do this separation, we can just integrate here. We can just slap an integral symbol on both sides. So here we have the integral of some function of y, and that's equal to the integral of some function of x. So we integrate, and that gives us the integral of 1 over g of y dy equal to the integral of the function of x dx. So we solve both of these integrals. One of them will be in terms of y, the other in terms of x. And then when we've done that, we'll have an equation with x's and y's. No integrals, no derivatives. So with that equation for x's and y's, we solve for y if possible. Sometimes we won't really be able to solve for y, but if we can, we'll try to solve for y as a function of x. And this will be our solution. Once we've solved for that expression y, this will be the solution to the differential equation. Let's practice applying this technique to a couple of specific examples. So look first at example 1. We have this differential equation, and we just saw that this is a separable differential equation. We have a function of x times a function of y. So we can solve this using separation of variables. So for example 1a, we have the differential equation dy dx equals sine of x times y squared. The first step here is to separate the variables. I'm going to move the y squared to the other side, and then the dx I'll move to the right-hand side. So separating the variables, I'll have dy divided by y squared, and actually I prefer to write that as 1 over y squared dy. This equals sine of x dx. So once again, multiply both sides by dx, divide both sides by y squared. That separates the two variables x and y. Now that I've separated the variables, I'm ready to do the next step, which is just to integrate. So I integrate both sides here. I take the integral of 1 over y squared with respect to y, and the integral of sine of x with respect to x. The antiderivative of 1 over y squared, well, I want to think of this as y to the negative 2. So we take negative 2 plus 1 is negative 1 divided by negative 1. We'd have y to the negative 1 divided by negative 1, or we can write that as negative 1 over y. So that's the antiderivative of 1 over y squared. And if this looks a little bit uncertain to you, if you're not quite sure how I got from the antiderivative of 1 over y squared to this negative 1 over y, then please pause the video, take a second, and write out all the steps here. We've seen this integral before, but it's worth really being comfortable with this. You'd first write this as y to the negative 2 dy, then take the antiderivative using the power rule. Notice that we don't have a natural log here. It's not natural log of y squared. That's not the correct rule. So take a second, make sure that you're comfortable with finding the antiderivative of 1 over y squared, and then we'll continue. So we have the antiderivative of the y function, and then the antiderivative of the x function is negative cosine. Negative cosine, and we're doing indefinite integrals here. So both of these would have a plus c, but I don't want to just write plus c on both sides because it's not necessarily the same plus c. This could be any arbitrary constant. So I could write like plus c1 and then on the other side plus c2. That would be okay. But I could imagine taking this c1 and moving it to both sides. So I'd have c2 minus c1, and then this expression right here is just some arbitrary constant. So instead of writing a constant on both sides here, I can just write an arbitrary constant on one side. So we'll just write plus c on this side of the equation. So we don't have to write plus c on both sides because we can just imagine moving the arbitrary constant from the y integral over to the other side, and then we just have some other arbitrary constant. So here's our expression after integrating. The very last step is to solve for y. So I'm going to multiply both sides by -1. And then -1 times -1 over y is just +1 over y. And I could think of multiplying -1 times this arbitrary constant, but this arbitrary constant is positive, negative, or 0. It really doesn't matter. So I'm just going to write this again as cosine of x plus c. It's really negative of the c that we had before, but it's just an arbitrary constant. It's positive, negative, 0, so I can write plus c, and this could be any negative or positive number. One more step to solve for y. I'm going to take the inverse of both sides. So y equals 1 over cosine of x plus c. This is the solution to the original differential equation. So now that we've found this solution using separation of variables, let's go ahead and verify that it actually worked. Let's check to see that this is indeed the general solution to the differential equation. So we want to take the derivative, and then we're going to see that the derivative equals sine of x times the function squared. So in order to do this, it helps to rewrite the function a little bit. Let's just write this as cosine x plus c raised to the -1 power. Now we need to find the derivative here. So y prime, this is going to involve chain rule. We take the derivative of the -1 power, we'll bring that out front. So we have negative times cosine of x plus c raised to the -2 power times the derivative of cosine, which is negative sine of x. And we can simplify this a little bit. We have negative times negative, and then raising to the -2, that's the same as dividing by the whole thing squared. So I can write this as sine of x divided by cosine x plus c quantity squared. So this right here is y prime. Okay, now this is the left-hand side of the differential equation. We can just write that in here right now. That's the left-hand side of the differential equation. Let's take a look at the right-hand side of the differential equation. Remember, we want to handle these two sides separately. We don't want to set them equal before we've actually showed that they're equal. So on the other side of the differential equation, the right-hand side, we have sine of x times y squared. Well, here's y, so we're going to square that. So we have sine of x times 1 over cosine x plus c squared. Or, what's another way that we could write this? 1 divided by cosine x plus c squared. Notice what we have here is the same on both sides of the differential equation. So, separation of variables worked. We found the correct solution to this differential equation. Let's take a look at this in Desmos compared with a slope field. So here's our slope field generator in Desmos, and we're going to put in the differential equation here. We have sine of x times y squared. So there's the slope field that we're looking at for this differential equation, and we just found the general solution. It's y equals 1 divided by cosine of x plus c. Now, if we add values for c, we can see what the different solution looks like. So let's go ahead and look at a range here from, let's do -10 to 10. And if we look at the different expressions here, we can see that these solution curves are matching the slope field. These are really cool. Isn't that cool? We just have these really wild looking solution curves here. So here's the general solution to this separable differential equation. Let's take a look at example 1b. And this should look familiar. Here we have the differential equation y prime equals y. And we've seen the solution for this already. This is the function whose derivative equals itself. And we can express the solution as any constant times e to the x. Now let's see how to analytically find that solution here. So we start with the differential equation. Y prime equals y. And let's write y prime as dy over dx so we can think about the separation of variables here. Now, we want to make sure that this is a separable differential equation. And a separable differential equation means that we have the derivative equal to a function of x times a function of y. But I don't see a function of x here. Well, that's not a problem. We really could just put in 1. And then we have a function of x, which is just a constant, times y. So we can still separate here and solve using separation of variables. I'm going to divide both sides by y and multiply both sides by dx. So to separate here, I will have 1 over y dy equals 1 times dx. I've successfully separated the variables. All of the y's on one side, all of the x's on the other. Now I can integrate. The antiderivative of 1 over y is the natural log of the absolute value of y. And the antiderivative of 1 Well, think of what function has a derivative of 1. That function is just x. We have indefinite integrals here, so we need to add plus c, and once again we only add the plus c to one side. So here we have it. Now we want to solve this expression for y. So how do we solve for y here? Well, we take both sides and we raise e to the power of both sides. So e raised to the natural log absolute value of y equals e to the x plus c. Since these two sides of the equation are equal, I know that I get the same thing if I just raise e to the power of both sides. And on the right-hand side here, we can write this as e to the x times e to the c. Now, let's think about this arbitrary constant c. When we have the original integral, this arbitrary constant c can be positive, negative, or 0. So this can be plus or minus, or it could be 0. Now, take a look at this constant here. C is still positive or negative or 0, but when we take e to the power, this all of a sudden is always positive. So think about the function e to the x. If we were to graph that function e to the x looks like this, and no matter if we plug in positive values of x or negative values of x or 0, we always get positive outputs. So e to the c is always positive. And let's rewrite this a little bit. Let's just write this as a times e to the x. So I'm just rewriting e to the c as a, and we're thinking of a here as an arbitrary positive constant. So a, once again, is always positive. So when we take e raised to the natural log of y, those cancel, and we're left with the absolute value of y. And we want to keep the absolute value bars. This is important. So the e and the natural log undo each other, and we're just left with the absolute value of y. And that equals a times e to the x. A is an arbitrary positive constant. Now, I want to still just solve for y. Here I have the absolute value of y. I want to get just y equals. So to solve for y, to get rid of these absolute value bars, I just add a plus or minus to the other side. So I can write y equals plus or minus a e to the x. So now, remember the context of a. A was an arbitrary positive constant. Now we have an arbitrary positive or negative constant. And we want to know, could this constant also be 0? So we have an arbitrary positive constant, and then we take a plus or minus here, so we have an arbitrary positive or negative constant. We want to know, could a also be 0? So if a is 0, then the function y would just be 0 times e to the x, so y would be 0. We want to know, is this a solution to the differential equation? If this is a solution to the differential equation, if y equals 0 is a solution, then this constant a could also be 0. Well, let's see. What's the derivative of 0? The derivative of 0 is just 0. So we'd have 0 equals y, but if y equals 0, then we have 0 equals 0. So yes, y equals 0 could be a solution to the differential equation. So all of this thought process here behind looking at this constant a, seeing if it could be 0, this is only so that we can say this arbitrary constant could be positive or negative or 0. So our final answer here, we can write y equals any arbitrary constant times e to the x, and let's write in the context here, this arbitrary constant c can be positive or negative or 0. So this is the normal way that we think of the arbitrary constant c. It's positive or negative or 0. So here is our final answer. The solution for this differential equation is y equals a multiple of e to the x. Let's solve example 1c. Here we have the differential equation y prime equals x plus y. And as written, this is not actually a separable differential equation. We don't have a function of x times a function of y. We have a function of x plus a function of y. So this is not separable. So we'd like to think that, well, maybe we couldn't solve it using separation of variables. But we still can solve it by using a special little technique here. I'm going to make a simple substitution. I'm going to say, let's let some value, we'll just call it r, be equal to x plus y. So I'm just redefining x plus y to just be this one single variable r. This substitution might seem a little bit arbitrary. How does this help us? Well, consider taking the derivative here of both sides with respect to x. So we have the derivative of r with respect to x, And taking the derivative of the other side, the derivative of x with respect to x is just 1, and the derivative of y with respect to x is dy dx. Now dy dx, that's y prime. And dy dx originally was equal to x plus y, but we could also say that dy dx equals r because we set r equal to x plus y. So instead of having dy dx here, we could call this dy dx just r. So let's trace through this again. We set x plus y equal to this value r, so x plus y equals r, but x plus y was the same as dy dx. So dy dx here we can replace with r. So we can write this as 1 plus r. Now we have this differential equation, dr dx equals 1 plus r. This is a separable differential equation. We have the value r instead of y, but now we can divide both sides by 1 plus r, and we can solve this. So we write 1 over 1 plus r dr equals 1 times dx. So we've separated the variables. Now we can integrate. The antiderivative of 1 over r with respect to r is simply the natural log of the absolute value 1 plus r. And this equals the antiderivative of 1, which is just x. We can solve here for r just like we solved for y in the previous problem. We'd raise e to the power of both sides, and then we have absolute value of 1 plus r equals, well, we'd add a plus c here, and then we have some constant times e to the x, and this was an arbitrary positive constant. To get rid of the absolute values, we add a plus or minus, and ultimately we can just say 1 plus r equals some arbitrary positive or negative or zero constant times e to the x. Solve for r, and we have c e to the x minus 1. Okay, so what does this do for us? Well, remember, r was equal to x plus y. So I can write this as x plus y equals c e to the x minus 1. Solving for y, I have c e to the x minus 1 minus x. And this is the general solution to the differential equation. So I think this is kind of cool. Even though we didn't have a separable differential equation to start with, we could still do this substitution trick and still find the general solution for the differential equation.